Before we begin trying to prove various facts about summations, we're going to comment on some properties that we could prove using that definition. But for now, we'll take for granted that these things work. We may revisit this later and try to prove that these properties hold. But for now, again, we're just going to assume that this is reasonable. The first property here is that if you have a summation of an expression that involves addition, you can split it up across the addition and factor out constants. This follows from our basic properties of addition and multiplication, things like the distributive property, the fact that we can associatively add up different numbers in different orders. All of the standard properties of numbers is what you would use to prove this. Again, for now, we're not going to do this. Notice that when we distribute the summation, the only thing that really changes is that we get two summations and we factored out constants. This allows us to ignore some details, and we actually did something similar earlier when we computed one of our summations. The bounds of the summation remain unchanged when you do this. You're just splitting up the summation and adding it up in a different way. Another exceedingly useful property of summations is that you can split them in the middle in some sense. What I mean by that is if you're adding up numbers from m to n, you can split it as some value k that lies between them, and have two different summations that add up the first part of the terms and the second part. So notice that we split the summation so that we are adding up the first m through k things, and then we add up the k plus 1 through n things. We're still adding up the same values, we're just adding them up and grouping them in a particular way. This will turn out to be very helpful in our proofs. This and the first property are the crux of what we're going to do with summations for the most part. One final useful property of summations is that if you have a summation that does not start at a value that you desire, you can rewrite it as two different summations that do start at that value. Rather than having to derive a whole bunch of different formulas for different starting values, we're going to, in general, try to derive our formulas such that they start at 1, and we will assume that going forward. So, when we have a summation from m to n, we can write it as a summation from 1 to n minus a different summation from 1 to m minus 1. Why on earth is this true? I'll write this out with a numerical example. The other ones most people are okay with. You're just splitting up numbers in particular ways. This one seems a little suspicious. So why is this true? If I want to add up the numbers 4 plus 5 plus 6 plus 7, one way to add that up is to add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, and then subtract away all the numbers I do not want to add up. So I'm going to subtract away 1 and 2 and 3, and now the 1, 2, and 3 will all cancel out, and I'm left with what I started with. Again, this will be useful because our formulas that we are going to derive for summations are going to critically rely upon the fact that the summation starts at 1, which is going to be important for analyzing these things. So being able to use this will allow us to use those formulas in a more convenient way when our summations do not start at 1.